Hi guys, this is the last section of chapter 11. It finishes up our surface area and volume of solids. So, since the quarter started, we've been on school closure here. We've done chapter 10, which dealt with area, so just area of geometric shapes, and now chapter 11 has been surface area and volume of three-dimensional shapes. So this will wrap it up here for chapter 11. Similar solids, we talked about similar polygons. Here's what it means to be a similar solid. It's two solids that have the same ratio of measurements. So to decide if two solids are similar, we have to look at the ratio of their sides and make sure that they are in the same ratio, like any of their corresponding sides, just like we did with two-dimensional shapes. So if you look at example A, you can see that if you multiply each of these by 2, the scale factor of 2, you get the corresponding side. Oh, we don't. We miss one here. So we get a 4. This should be a 4, and it's a 2. So the first set is not similar. You can just write not similar. If you look at the second one, on the other hand, multiply each of these by 2. You'll notice that you get the 4, and the 6. So these are similar. And the ratio of their sides, you just take any set of corresponding sides. You could take 3 over 6 and reduce it. So 3 over 6 equals 1 over 2. So that's the ratio of their sides. Ratio of their sides here. Sides ratio. Let's go up here. Area ratio, and then volume ratio. Here's how it works. We did this lesson just before going on our little closure here. But sides, we've got 3 over 6 is 1/2 reduced. Area, remember we square the ratio of the sides. So 1 squared over 2 squared gives us 1/4. And for volume, we've mentioned this, but here it is. Volume is 3-dimensional, area is 2-dimensional, and sides or length are 1-dimensional. So volume is 1 cubed over 2 cubed, which is 1:8. So there's our ratio for volume, ratio for surface area, ratio for sides. That's how they're all related. But similar solids works kind of similar to similar polygons. You're looking at all corresponding side lengths, making sure they're in the same ratio. If even one differs, they are not similar. Similar solids theorem says if two similar solids have a scale factor of a to b, then the corresponding areas have a ratio of a squared to b squared, and corresponding volumes have a ratio of a cubed to b cubed. It's just extending the theorem that we saw earlier on. It says the boxes are similar with a scale factor of 1 to 3. So their scale factor, or one-dimensional, we'll call it 1D, scale factor is 1 to 3. Find the surface area and volume of a box G if box F has a surface area of 24 square feet and a volume of 7 cubic feet. So we're going to set up a proportion. Before we do that, we're going to get our 1D, 2D, 3D ratios using this theorem up here. So there it is, square A, square B. So we've got 1 squared to 3 squared, which is 9, and then 1 cubed to 3 cubed, which is 27. That's our 3D one. So we grab this 1 to 9 ratio. 1 is to 9 as surface area of box F. Box F is the smaller one. So box F has a surface area of 24 square feet. So the 24 is going to go on the top to correspond directly with the smaller of the two numbers in the ratio. What we're looking for is the big S surface area of box G. So you cross multiply, S times 1 is S. 9 times 24, 180 plus 36, we got 216 square feet. All right, 3D. 1 is to 27, so we're going to take that 1 over 27 And it says that box F has a volume of 7 cubic feet. So box F is a smaller one, and 7 will go up here. Put big V down here for volume of G. Cross multiply, V equals whatever 27 times 7 is. That's 140 and 49, 189. And that is cubic feet. So there it is. So that's using that ratio. We just extended this now to cubic. All right, thanks for watching.